Today, we're diving into an invisible force, one that's shaping every single breath you take, whether you're standing on a mountain peak or, just sitting on your couch. We're talking about Dalton's Law. You've probably felt it, right? That thin, kinda unsatisfying breath you take at high altitude compared to the rich, heavy air you feel by the ocean? Well, that's not just in your head. And the reason for it is a really cool, fundamental law of physics. Let's get into it.
So to really get a handle on that feeling, we first have to understand the air that's all around us. Think of this as like the instruction manual for our atmosphere.
Okay, so here it is in all its glory, Dalton's law of partial pressures. And you know what? At its core, it's actually super simple. All it's saying is that the total pressure you're feeling from the air isn't coming from just one thing. It's the result of a whole bunch of different gases all pushing together.
Here's an easy way to think about it. Imagine you're at a loud party. The total noise isn't just one big sound, right? It's the sum of the chatter from that one group over there, plus the laughter from another group, plus the music in the background. Well, the gases in the air work the exact same way, but with pressure instead of sound.
And when you put it into the language of science, it looks just as simple as it sounds. P total, that's the total pressure, is just the pressure of the first gas, plus the pressure of the second gas, plus the third, and on and on. Each one just adds its own little piece to the grand total.
Okay, so let's make this personal. We're going to go from this general scientific law to the air you are literally breathing in right now.
So take a look at what our air is actually made of. It's not pure oxygen, not even close. It's about 78% nitrogen, which, honestly, our bodies pretty much just ignore. The part we really need is that 21% oxygen. And the rest? Just a tiny little sliver of other gases.
Now let's put a real number to that total pressure we've been talking about. At sea level, the weight of all the air piled up on top of us creates a pressure of about 760 millimeters of mercury, or mmHg. Don't worry about the units, it's just a standard way to measure pressure, like feet or meters for distance. So 760 is our starting point.
And this is the key. Our bodies don't really care that the air is 21% oxygen. What they desperately care about is the partial pressure of that oxygen. So if you do the math, 21% of that total pressure of 760, you get about 160 millimeters of mercury. That number, 160, is what matters for survival. It's the amount of push oxygen has to get from your lungs into your bloodstream.
But what happens when that crucial number changes? Well, this is where Dalton's law suddenly goes from being a neat science fact to being a matter of life and death.
Let's look at two totally opposite situations. Go up a mountain and the total air pressure drops. The air is still 21% oxygen, but because the total pressure is lower, that oxygen push, its partial pressure, is too low for your lungs to grab it properly. That's hypoxia. Now let's go the other way, deep sea diving. The huge pressure from the water makes the total gas pressure skyrocket. This makes the partial pressure of nitrogen so high that it can actually start to mess with your brain, a dangerous condition called nitrogen narcosis.
Understanding these extremes isn't just for mountain climbers and scuba divers. This very same science is being used in hospitals every single day to save people's lives.
So think about this. When a doctor gives a patient oxygen, they aren't changing the room's air pressure. What they're doing is changing the percentage of oxygen in the air the patient breathes. And because of Dalton's law, that cranks up the partial pressure of oxygen, giving it a stronger push into the blood. It's the exact same principle behind breathing machines like CPAPs. And it's how they treat decompression sickness, the bends. They put a diver in a high-pressure chamber and carefully play with the partial pressures to let the dangerous nitrogen bubbles safely dissolve and be breathed out. It is all about managing those individual gas pressures.
All right, so we've gone through the science, the biology, and the real-world applications. Let's boil this whole thing down to one single idea you can take with you.
This is it. Simple, right? The big push is just the sum of all the little pushes. That one simple rule explains everything from feeling breathless on a hike to how a doctor helps a patient breathe easier in a hospital bed. So that's Dalton's law. It's pretty amazing when you think about it. We're all walking around in this perfectly balanced, invisible system that literally keeps us alive from one moment to the next. And it just makes you wonder, right? What other invisible laws are quietly running the show all around us?